So glad to see that you're back. So let's go for David's third lecture.
I think it's on now. Yeah. Okay. Great. Yeah. So yesterday we were halfway through discussing weak lensing. We talked about the lensing distortion tensor and what that does to images of galaxies or anything else. And so I wanted to start getting into the weeds of cosmic shear, where cosmic shear, well, we saw shear was one of the components of the distortion tensor that just changes the shapes of whatever images you're looking at. Cosmic shear is also the name that we give to just the idea of getting lensing from the shapes of galaxies, right? So this, whenever you hear cosmic shear, just think of weak galaxy lensing, right? Where the source is a galaxy. All right. Right. So how does that work? So what do we measure? What we measure is, for a given galaxy, we will measure its observed ellipticity. And what we said is that that is the true ellipticity, which I'm going to write as EIN. Remember, I is either 1 or 2, because there's 2 components to the ellipticity. And so this would be the true unlensed ellipticity of the galaxy plus a contribution coming from weak lensing, which is just the shear component of the distortion tensor. Okay. So this is the intrinsic galaxy shape as you measure it, where in practice, we will see that what you measure is not just the intrinsic galaxy shape plus lensing, but also any source of noise in the measurement of that shape. But just think of this as the true unlensed shape for now. So in practice, what does that look like, right? Let's imagine that you've observed a pixel in the sky. So this is just some tiny region in the sky where you have a bunch of galaxies, and for each galaxy, you may have, at the position of each galaxy, you may have the corresponding value for the shear field, right, which I'm going to write as a rod, meaning an ellipticity pointing in a particular direction, right? So let's say this is the shear component, and the shear component will be correlated across this pixel because it's all caused by the same intervening large-scale structure over here, and you're observing from over there, right? But what you observe is not just this, it's this plus the intrinsic shape. And so the question is, in the same pixel, how different the intrinsic shapes are from the cosmic shear. And it turns out that cosmic shear, compared to the typical ellipticity of a galaxy, is a very tiny component. So the typical shape of a galaxy will be actually, the typical ellipticity will be quite large compared to the cosmic shear, right? So for each of these galaxies, you'll have a different ellipticity that is much larger than the shear component, okay? And it's the sum of these two that will give you the actual measured value for the thing that you're actually measuring, right? So what you do is the main assumption is that the intrinsic shapes of galaxies are uncorrelated, right? So the shape of a galaxy here, and here, they have nothing to do with one another. And the only thing that will correlate them is the cosmic shear. So what you do is you say, okay, I don't care, I'm going to try to average down this noise by just taking an average over all these galaxies and just getting a single measurement of the shear effect at the center of this pixel, let's say. And the hope is that you have a large enough number density of galaxies that you can average down this noise, right, and get a measurement of the average shear within that region. So that's kind of the idea. And we'll see how problematic these intrinsic shapes are later on. But for now, let's imagine that we can do this, right? We can make a map of the cosmic shear for all the galaxies in our survey. We said, because it's a bit annoying to have to deal with 2 components of the cosmic shear. Cosmic shear comes from the same single scalar quantity as for example, the lensing convergence, which is the lensing potential, right? And so let's think of the lensing potential, sorry, the lensing convergence itself. Let's imagine that instead of measuring shear, what we're measuring is actually the convergence. This is just because it's going to make the math a bit easier. But none of the conclusions and kind of ideas that we're going to show here actually change that much. Maybe in the last lecture we can introduce some of the subtleties of going from shear to convergence. But for now, let's imagine that we can actually just measure this directly from these observations. We can transform basically our measurements of gamma into kappa, and that's actually true. Okay, well, let's take a simplified picture in which all of our galaxies are sitting at the same distance from us, right? So this is the distance to the source is the same for all our galaxies. And then in that case, we worked out yesterday where the corresponding convergence would be, right? It's just given by this integral along the line of sight of the matter density fluctuations times this kind of radial function here, which came from the lensing equation. All right, but that's not actually how reality works, right? We don't have all galaxies lying at the same redshift. Usually what we have is, as a function of redshift, you have galaxies lying in some kind of range of redshifts, right? So some kind of bin of redshifts with a given redshift distribution. Let's say this is P of Z. Meaning the distribution of redshifts of your galaxies. All right, but then that doesn't change things too much, right? So the kappa field that you would measure from all of these galaxies, now it wouldn't be the kappa at a particular redshift, but the average of all the kappas at different redshifts, right? So this would be just an integral over all possible redshifts of the P of Z times the kappa at that particular direction in the sky for sources at a redshift Z, okay? So it's basically this for sources at a given distance, right? So that's the thing that I'm inserting in that other equation, right? So if we do that, what do we get? We get 3/2 h naught squared omega m times an integral from 0 to infinity dz P of Z times an integral d chi from 0 to chi of Z of chi divided by the scale factor at that value of chi times chi of Z minus chi divided by chi of Z. And then times delta of chi n Z of chi. All right. So in principle, that would be it. That's the quantity we're calculating. Does that make sense so far? The problem with this expression is that if we want to eventually make a theoretical prediction for this, it's kind of annoying because the quantity we care about, this one, is embedded in two different integrals, and that's a bit annoying. So instead, what we can do is change the order of integration. And this is something that you learn to do in the first year of maths, if not earlier. So I'll let you do that yourselves as a problem. So if you change that order of integration, you get a simpler integral, which looks like this. So it's an integral along the line of sight of a radial kernel that I'm going to call the lensing kernel times the density, the overdensity field, kappa n, comma z of chi. Okay? And this lensing kernel is something that you can just compute externally. QL of chi is 3/2 h naught squared omega m times chi over a of chi, and then the integral from z for that chi to infinity dz prime p of z prime. And then I'm going to go into the other board. 1 minus chi divided by chi of z prime. So that looks like a complicated equation, but we can actually make sense of it. So at a given distance chi, this lensing kernel is the integral of the P of Z times some function. The P of Z integrated from the redshift corresponding to this distance all the way to infinity, right? So that means if we were here, for example, let's say we're here, that lensing kernel should be what? 0? Yeah, 0, because P of Z at all those redshifts is just 0. It's beyond, we're beyond the P of Z, right? So here it will be 0, 0, 0. So it will be 0 up until the point where we get to P of Z, right? And then it will start picking up, and then eventually die down like that, right? So this is the shape it has, right? It's very similar to the shape that this function itself has, this one here. And that's, if you plot this is a second-order polynomial in chi. So it's basically a parabola that looks like this from the sources. So this is the position of the source to 0. It's basically a parabola. That's what this kernel does. This is essentially the same, except now your sources are a bit diffused. They're not exactly at the same redshift. So at the beginning, it won't be exactly a parabola. It will basically follow the redshift distribution, but then keep going like a parabola all the way to redshift 0. So this is the Q. This is QL, right? QL of Z, let's say. And then we can wonder, does that make sense, right? That means that kappa receives contributions from all redshifts, from the redshift of the sources to 0, right? Does that make sense? So it's affected by the large-scale structure all the way along the line of sight. That's what you would expect, right? That's what lensing does. Lensing will deflect photons through all of the large-scale structure from the sources all the way to you, right? So that's why the lensing kernel has this shape. It basically tells you what the contribution from different points along the photon trajectory is, right? Okay, and this will be quite important, actually, to understand why weak lensing is so sensitive to small-scale structure. So we'll come back to this picture later on. P of Z? P will depend on the sample of galaxies that you have and how you've selected that sample, right? So if you have sufficiently good redshift measurements for your galaxies, you'll be able to select galaxies in a particular range of redshifts. So that means that you can isolate them to live in a particular region in redshift. If you have really poor redshift measurements for your galaxies, it will be difficult for you to locate them in a given region of space. So you might have a very broad redshift distribution, and you need to worry about how you estimate that redshift distribution. But we'll talk about that actually tomorrow. But yeah, yes. P of Z? Yeah, the assumption is that the assumption here at least is that whatever sample of galaxies you've selected, they've been selected in roughly the same way across the sky, so they have the same redshift distribution across the sky. Yeah. There's obviously this is something one should worry about, right? So if the galaxies you're using if the sample you're using is significantly fainter in a given region in space than other, you could imagine that the sample is actually different, so your redshift distribution actually varies across the sky. And you're not really sampling the same redshifts in this region or in this region. So then the total kappa field, the average kappa field, actually receives an extra contribution coming from spatial variations in the P of Z. And those can be relevant. If you have significant inhomogeneity in your survey, it can actually be relevant. Yeah. Other questions? No? Okay. So now we are working. This is the first instance of a field that is a projected field, right? Now we have a quantity that's defined on the sphere, the same way that Manu yesterday was talking about the temperature fluctuations of the CMB. This is a field now that is defined on the sphere. And in the first lecture, we saw how we deal with stochastic fields that are defined in 3 dimensions. Now we have to deal with the 2-dimensional ones. And it's good that Manu kind of did half of the work for me. So I wanted to take just a little bit of time to talk about stochastic fields. On the sphere, right? In S2. I'm going to skip a lot of the stuff that I had written here, because actually Manu talked about a lot of this. But the idea now is the same treatment that we had for fields defined in 3 dimensions. Now we need to think about fields defined on the sphere. So, we talked about stochastic fields in 3D, just thinking of them as vectors of multiple random variables characterized by a given multivariate distribution of them. This is exactly the same idea, except these points are now the points within a sphere, so nothing changes in that picture. You can still think about statistical isotropy, right? The idea that the sky should be the same no matter where you look at, but also in which orientation you look at the sky, so whether I tilt my head like this or not. And that will involve, that will imply certain things about this, right? So for example, what would the 2-point function between 2 fields defined on the sphere at positions n1 and n2 be n2, right? If we have statistical isotropy, this 2-point function should only depend on what? Yeah, the relative angle between the 2 points, right? And that's given by so this should be some function that only depends on essentially the cosine of the angle between the 2 vectors, so n1 dot n2, basically. So that's the only way that things should depend. So this is what you would call the correlation function, AB. All right. And another thing that we saw was a nice thing to do for fields defined in 3D is to take their Fourier transform, right? For fields defined on the sphere, Manu already told us the sensible transformation to do here is the spherical harmonic transform. So we define the spherical harmonic coefficients ALM as being the integral over the whole sphere of A of n times the spherical harmonic coefficients, YLM of n, complex conjugate. And then the inverse transform is just basically the expansion of your field into spherical harmonics. So sum over all the L's from 0 to infinity, sum over M from minus L to L. And you've seen all of that in quantum mechanics, if not in many other areas, of ALM times YLM. Okay? It's kind of the analogous of a Fourier transform and an inverse Fourier transform. And Manu yesterday introduced this in the flat sky approximation, where you can actually replace this by Fourier transforms and inverse Fourier transforms in 2D. And what I would say is the main thing to bear in mind is that this is, you can think of a spherical harmonic transform in almost exactly the same terms as what you would think of Fourier transform. You can identify L as the modulus of a wave vector in 3D, or in 2D in this case, right? So just think of it as essentially a wave vector, meaning an inverse wavelength. But now these are wavelengths defined on their sphere, so they're angular wavelengths, I guess. So angular separations corresponding to a typical kind of, let's say, wavelength on the sky associated with a given L. Manu had a 2 pi. I like to think of pi instead, but it doesn't really matter. It's on an order of magnitude, right? So that's how you relate an L to a given typical angular separation or angular scale that the spherical harmonic is probing. Okay. All right. And so the same way that we have a consequence for statistical isotropy and homogeneity in the 3D case, we have another similar consequence in terms of the spherical harmonics of fields in 2D, which is how we define the angular power spectrum. So the idea is that if you have statistical isotropy, and you look at the correlator between ALM and B, L prime, M prime, complex conjugate, this has to be proportional to the Kronecker delta LL prime and MM prime. So different harmonic coefficients should be uncorrelated to one another if you have statistical isotropy. And the proportionality constant is what we call the power spectrum, CLAB, which only depends on the modulus of the wave vector, meaning the L harmonic number. right, so this is all stuff that Manu talked about yesterday, I think. Any questions about any of this, interpretation of this or anything? No? What's interesting, I think, is how we connect these angular power spectra, which are the things that we're going to be able to calculate for things like the convergence field, how we relate that with the physical quantities that we care about, which are things like the overdensity, matter overdensity, right? So in general, let's think of a projected field like this, AFN, which can always, or often, it can be written as a line-of-sight integral of some three-dimensional field, right? So we can always write this as some kind of integral along the line of sight of a kernel associated with that quantity times a 3D quantity, so something defined in 3 dimensions, evaluated along the light cone, like that. Okay? So this is what we can observe. This is what we would like to observe, right, or what we would like to have access to. So the question is, how do we relate the statistics of this field to the statistic of that other field? And in particular, we care about the angular power spectrum. So let's say we're looking at the angular power spectrum between field A and field B. So the relation between this angular power spectrum and the corresponding 3D power spectrum of the 3D quantities is given through something that we call the Limber equation. Which is given by an integral along the line of sight divided by chi squared. Then the radial kernels of the two quantities that you're correlating, QA of chi, QB of chi, times the 3D power spectrum of the corresponding 3D quantities. So I'm going to write that as PAB of K and Z. And then the question is, what's the 3D wave number? How does it relate to the 2D wave number or the 2D multiple? And that's through the relation that you saw yesterday from Manu's slides. So K can be related to a 3D wave number can be related to a 2D one by simply dividing by the comoving distance to the quantity that you're looking at, right? A more accurate version of this is that this should be L plus 1/2, but this 1/2 doesn't really matter if you're at sufficiently high L, which will be the case for the most part. This is the Limber equation. I haven't derived this at all, right? So if you want to look at the derivation of this, I can give you references for that. And in fact, this Limber equation is an approximation, right? So it's not. This actually is an approximation. The exact equation is a bit more. It's a bit longer. It involves Bessel functions that complicate its expression a little bit. So, and I'm not gonna. I don't think it's worth the time to discuss that in much detail. For most of what we're gonna discuss, the Limber is an appropriate approximation. Cases in which you will have to worry that Limber is not good enough is when the width of these radial kernels. So let's say that you have a radial kernel like that, and the typical width of this radial kernel, if that width is comparable to the typical correlation length of the quantities that you're correlating, right? So if we're thinking about the matter distribution, we saw, the matter correlation function kind of dies down at separations of a few megaparsecs, let's say 10 megaparsecs or something like that. So if you have a kernel that has a width of a few tens of megaparsecs or smaller, then Limber is going to fail miserably. So this will be a very bad approximation. For the most part, we have kernels that span several hundreds of megaparsecs, where the correlation function is essentially 0 or very, very small. So Limber is a good approximation for most of the observables that we're going to look at. Okay. So that's why I don't want to go into the details of the non-Limber stuff. And also, Limber is really useful because it will give us intuition about which scales. Which physical scales are actually contributing to the different observables that we will look at, and we'll talk about that later on. Does that make sense? Any questions so far? Okay. Yes, that's right. Yeah, yeah, yeah. The question was just to make sure, I guess, that if your redshift bins are really, really tiny, right? So if you progressively make them smaller, then Limber will start failing, and the answer is yes. You should worry about, typical redshift bin, delta Z of about 0.01, I think that's about 30 megaparsec. That's definitely going to start failing the Limber approximation, right? So whereas if you have bins of 0.1, it's probably fine. Yeah. And it will, so Limber will start failing at the lowest multiples first, and then it will progressively go to the higher ones. So even you can probably get away with Limber if you're really interested in the smallest scales, right? The largest multiples. So it will start failing. I'm not sure what I said before. It will start failing on large scales, meaning the smallest multiples, and then. But if you're interested in small scales, this, you can probably get away with it with Limber often. Yeah. Okay. Great. Okay. So then, how do we usually extract information from weak lensing? Usually, what we will do is we will have I'm going to use a different color for this. We will have samples of galaxies that we've selected at different redshifts. So we'll have what we call tomographic bins of galaxies, right? And we'll have made maps of the kappa field for each of them, and then we'll be able to look at auto and cross correlations of all those quantities. So the actual observable we tend to look at is the angular power spectrum in the kappa field and another kappa field at two different redshift bins. Let's call them I and J. So this is bin I, bin J, for example. So using the Limber equation, this is just an integral along the line of sight, d chi over chi squared. The lensing kernel for bin I of chi, the lensing kernel for bin J of chi, times the power spectrum of the three-dimensional field that lensing maps, which is the matter over density. So this will be then the matter power spectrum. I'm going to call that PMM of L over chi and redshift. Implicitly, redshift is the redshift corresponding to chi, okay? For reasons that have to do with mostly sociological tradition and how the field has evolved in large-scale structure, a lot of the early analysis, and even currently, I think I would say about 60% or so of all weak lensing analysis don't really use a power spectrum, but use the corresponding version of the correlation function. We saw that in 3D there's a relationship actually between power spectra and correlation function. So let me write that here for 2D in case you want to look at that. So the correlation function at a given angular separation theta is sum over all the multiples L, 2L plus 1 divided by 4 pi times the Legendre polynomial evaluated at cosine of theta times the CL. Okay, so that's how you relate one with the other. Remember, in 2D, sorry, in 3D, you had a Fourier transform relating correlation function, and CLs on the sky you have a transform in terms of Legendre polynomials. Okay. All right. Anyway, so often you'll see cosmic shear analysis being done in terms of correlation functions, and I just want to maybe, because we're going to keep talking about kappa, because I'm a power spectrum person, so I like to think about it in this case, but so that if you read the paper, you kind of know what they're talking about. I wanted to kind of clarify the usual notation that is used in those papers. So let's say that you have two galaxies, right, here and here, and now what you care about is correlating the value of the cosmic shear in these two galaxies, right? But then you need to worry about how you define the cosmic shear field itself. Is there a pointer somewhere? Yes. Right, so you have this galaxy and this other galaxy here. And so the question is, what's the natural set of coordinates that I should use to define the ellipticities of these galaxies, right? So if you have two galaxies, the natural, the line that separates the two galaxies, that gives you a clear preferred orientation with which to define your coordinates, right? So a natural set of coordinates would be to put one of your axes along this direction and the other one being the perpendicular axis, okay? Often, the ellipticities that you get for a given galaxy, they will not be given in these coordinates. They'll be given in sky coordinates, meaning x will be, usually x is right ascension and, sorry, no, x is declination and y is right ascension, usually. So you need to rotate the value of the ellipticities or shear that you get usually from in sky coordinates, rotate them to the kind of pairwise coordinate coordinate system, right? So that's, this is the transformation essentially that you would need to do to go from gamma 1, gamma 2, which are the field, the shear or ellipticity measurements in sky coordinates, to what's called gamma t and gamma x, which are, or gamma cross, which are essentially versions of gamma 1 and gamma 2 in these new coordinates. And here's the idea, right? So if you have a galaxy or a galaxy for which gamma t is negative, that means that its ellipticity is along the line of sight, along the line that connects it to another galaxy, right? That's a negative gamma t. A positive gamma t is when it's tangentially oriented. Remember that lensing causes this tangential orientation, so it makes sense that with this definition, positive gamma t should correspond to tangentially oriented things. And then gamma cross being positive or negative corresponds to ellipticities that are oriented about 45 degrees with respect to this direction here. And why 45 instead of 90 has to do with the fact that that cosmic shear is a spin-2 field, so it's basically, for a given galaxy, it's a rod rather than an arrow with a particular direction. So you can rotate this rod by 180 degrees and get the same rod again. Anyway, that's subtleties that I didn't want to get into. If you look at many cosmic shear analysis, things will be expressed in terms of gamma t and gamma x, and then what you care about is the correlations between gamma t and gamma x in two different galaxies, right? And that gives rise to two different correlation functions, what's commonly called psi plus or psi minus. And these are just the correlators of different combinations of gamma t and gamma x. So in particular, these are the correlators that you would look at. It's gamma t at n1 with gamma t at n2. And the logic is that n1 and n2 are separated by an angle theta, plus or minus gamma x at n1 and gamma x at n2. So these are the two different correlators that people usually look at. You might wonder how you could phrase this in terms of the convergence power spectrum, because that's what we're going to be talking about. And there's actually a relatively simple relation between the two of them. So it's an integral over all possible multiples, dl times L divided by 2 pi. The Bessel function, often called the cylindrical Bessel function, of order 2 plus or minus 2, sorry, minus plus 2 of L times theta times the kappa kappa power spectrum. Okay. So if you ever see or have to analyze data in the form of correlation functions, you can still just compute your power spectra, and in fact, that's usually the first step, and then translate them into correlation functions just using this expression here. This expression is actually a kind of flat sky approximation version of this other expression in terms of Legendre polynomials, so they're actually equivalent. Yeah. All right. Just wanted to dispel this because actually you'll see lots of papers that use this kind of notation. More and more people now are actually using power spectra to analyze cosmic shear data. So we'll continue working with that. Does that make sense? Questions? Yeah. Say again? No cross term. So there is a cross term, and that would give you another type of correlation function. For cosmic shear, you would expect that to be exactly 0. So you can measure that correlation function as a null test. So if that thing is not 0, that probably means that you have systematics in your data. Yeah. We'll talk a little bit more about that, because that's one of the diagnostics that you can do to see if you have problems in your data. Yeah. Yeah. Where does it come from? Why, in particular, look at this plus or minus that? Yeah, so the idea is that, as far as I understand, I need to remind myself of this. You look at these particular combinations. I think it's because those particular combinations will be they will not depend on the particular coordinates that you've chosen. I think I'm not completely sure actually. I'm not a fan of real space analysis, but I think that's the reason for that. But other than that, just chalk it up to tradition, and this is what people have been doing for a long time, basically. Yeah. No, so you will need to define them for each pair of points in your survey, right? So you would go over each pair of galaxies in your survey. For each pair, you would define the preferred coordinates like that, and then you would redefine the values of gamma t and gamma x for each of the two galaxies along this preferred axis. Compute this, and then compute these products, right? And then do this for all pairs of galaxies, and then average over pairs of galaxies. That's how you would. Yep. Yes, exactly. Yes. Yeah. Yeah. Exactly. Yeah. This is supposed to be observer here, and this is N1 and 2, basically. Yeah. Yeah. Great. Okay. So next, we're going to keep talking about things in terms of angular power spectra. But I wanted to mention this. So let's get back to power spectra, and let's start thinking about the main challenges that we have with cosmic shear. What are the main problems that cosmic shear needs to look at, or needs to be worried about? So first of all, as we said, what we measure is actually a noise-dominated signal or quantity, right? We said that for any given galaxy, the contribution from lensing to its ellipticity is usually much smaller than the raw ellipticity itself of the galaxy. And that's why we need lots of galaxies to average that down. Let's imagine that we had no lensing, right? So we had our measurements of the ellipticities were literally just the uncorrelated ellipticities of the different galaxies. That would mean effectively, we're thinking of this in terms of kappa, a measurement of kappa at each ellipticity, at each galaxy. That would mean we're measuring a value of kappa that is essentially uncorrelated across different galaxies. If I had to plot the CL kappa kappa in that case, what do you think that would look like? So that means the power spectrum of a signal that is completely uncorrelated across different points in the sky. Someone said 0. It's not 0. Flat. Why flat? So that's the right answer is that it would be flat. So anything that is completely uncorrelated across different points in the sky would be flat. But why should it be flat? We can maybe remember in 3D, there was a very simple relationship between a power spectrum and a correlation function, right? So a power spectrum would be the inverse Fourier transform of a correlation function, right? So it's something like, it's proportional to an integral over all positions in space of a correlation function as a function of that, right, of x. So what does the correlation function of an uncorrelated field look like? Sorry? What did you say? I think it makes sense that it should be 0. So if you're correlating a value of the field here and here, it should be 0. But if you're correlating a value of the field here and here, that should be something, right? Because the field itself will have some local variance, but it will be uncorrelated across different. So that means that this should be proportional to Dirac delta, right? At x equals 0, basically, right? So that, sorry, and this was this e to the I kx. I forgot about the vital part. Okay, but if this is just gets contribution from x equals 0, then this is equal to 1. So you get something that doesn't depend on k, right? The only dependence on k is here, and the only contribution comes from x equals 0. So right. So that's the way to see it, I guess. A power spectrum for an uncorrelated field is just a constant, and that also extends to the 2D version of this. It's just that it's a bit easier to think of this in terms of Fourier transforms. Okay, so we have white noise. This is what we call a white noise component, something that is uncorrelated across different points in the sky. So if we have a white noise component, it will look like a constant, right? In reality, we said our measurements are not just the noise-like shapes, but also the contribution from weak lensing to each of those shapes. And we haven't actually haven't shown you this yet, right? But we can think about what the power spectrum of this thing would be, right? It's something that needs to look like this, where this is the matter power spectrum. We'll see later on that leads to a shape that kind of looks like the matter power spectrum, meaning something that decays at high values of L, and then maybe might have some turnaround here, right? So it usually looks something like this. So this is the gamma part or the kappa part. So this is the signal. And this is the noise component. And so what that means is that for cosmic shear, but this is actually something that happens for any measurements, you will have a regime of scales where your measurements are dominated by the signal itself. That means that your measurement errors will be dominated by the uncertainty in the signal. This is what Manu called the cosmic variance source of the noise, of the measurement errors. And there will be other scales where you're dominated by noise, okay? And there's nothing you can do to reduce these errors when you're signal dominated, but there's definitely things you can do to reduce errors in the noise dominated regime. Basically, you want to lower this noise level as much as possible, right? So how do you think we can reduce the noise level for cosmic shear? What can we do about a survey of galaxies in order to reduce that? Get more galaxies, indeed, yes. So this noise power spectrum, let's call it CLN for noise, is basically, it has two components, right? So if we could measure the ellipticities really, really well, that should lower the noise. But also if we have more galaxies, we can average over more galaxies and get lower noise, right? So it has two components. So it's proportional to the error with which we can measure ellipticities squared. So this is the typical scatter of ellipticities divided by the angular number density in steradians, inverse steradians of galaxies in your survey. So if you have more galaxies, you lower the noise. If you have smaller measurement errors, then you also lower the noise, okay? And so you bring this down. The first measurements of weak lensing were in this regime, where the noise was up here, was actually much higher than the signal. So you could maybe see the signal on the largest scales after after measuring the power spectrum, but it was completely noise dominated. The error bars are completely noise dominated. For something like LSST, you expect to be in this regime, where this L here will be of the order of a few hundred, basically, let's say, order 200 or something like that. It probably depends on the settings that you're looking at. So that, L of 200, remember the corresponding angular scale is pi over L, so pi over 200. This would be in radians. If we do it in degrees, this would be about 180 over 200. So that's about 1 degree, okay? So that means that even LSST, which is one of the one of the newest and most advanced surveys, things will still, for cosmic shear, will still be noise dominated on relatively small scales. That doesn't mean that we can't measure the small scales. It's just that the error bars in our measurements will be dominated by noise rather than signal, right? So this is, I think, one of the most important drawbacks of cosmic shear is that it's very difficult to not be noise dominated. It just, there's a lot of noise, so you just need to accumulate as many galaxies as possible. And one, just to give you an idea of how that has evolved over time, this is a picture of different galaxy surveys. Thanks a lot. As a function of two of the main variables that we care about. So it's on the x-axis, you have the volume of space that they cover. So the larger the volume, the better your power spectrum measurements will be. But also the source density, right? So that tells you how many sources you have to average down the noise. And so stage 3 surveys, currently, the ones that we currently have, DES kits, some of you might be involved in those. They're in this regime, fairly large volumes, but still, relatively low number densities. When we say low number densities, they're actually quite high number densities. This is 10 galaxies per square arc minute. An arc minute is very small, and you have 10 galaxies per square arc minute in those cases. So you're talking about of the order of 1 billion galaxies in the case of DES or something like that. And we want to move to this other regime, right? LSST, Euclid, potentially the Roman Space Telescope, where the typical source density is about 3 to 4 times larger, and you cover a much larger portion of the sky. That will, as I said, this will lower the noise, but it will not bring you to the level where everything is signal dominated. You would still have to deal with quite a lot of noise. Okay. Yep. Yeah, I think it probably depends on what was assumed. I think this probably is. I would need to check how this figure was generated. This is in the weak lensing review that I recommend you look at if you're interested in weak lensing from this year. My guess is that this corresponds to the target depth of LSST. This might be the actually realized depth of HSC, meaning the depth that they could use for their weak lensing analysis, which is always lower than you think, right? So you might think that you can go to magnitude 27 or something like that. In reality, HSC uses magnitude 24.5 or something, so that means significantly lower number density. That's my guess, but it's true that HSC was supposed to be almost as deep as LSST. So yeah, so it might be that in the end we're in this regime instead of that regime, right? So it will depend on the cuts that we need to do on the real data to get it to that level. Yeah. But that's a very good question. Okay. So that's challenge number 1, is we need to deal with a lot of noise. Challenge number 2, which was asked about a couple of times already, is we've been saying that this noise component here is flat, it's completely uncorrelated, so we just need to estimate it this way and subtract it from our measurements, and we're done with it. By the way, I didn't say the intrinsic ellipticity of galaxies is of the order of 0. So the scattering that ellipticity is 0.27 or so, right? Whereas the cosmic shear component is percent level. Yeah, so that's why it dominates so much. Anyway, but we said, what if these shapes are actually correlated with one another, right? Couldn't it be that the actual intrinsic shape of the galaxies are correlated? You could imagine that there might be some physical processes that align galaxies that are nearby with one another, right? So that's the other challenge, one of the other challenges that cosmic shear needs to deal with, which is intrinsic alignments. That means the fact that the intrinsic shapes of galaxies might actually be correlated with one another. I didn't, that's okay. Right, so let's split EN, so the intrinsic measurement, the intrinsic ellipticity of a given galaxy into 2 components. One of them, which is correlated with the large-scale structure, I'm going to call that EI for intrinsic. And then I'm going to call the remainder, I'm just going to call it noise, n. So the, the component of the electricity that doesn't really correlate across different galaxies. And so what physical processes could lead to a correlation between the shapes of galaxies that are close to one another, all right? Or the correlation of the ellipticities of galaxies with the large-scale structure, okay? And so the simplest model that can give us that is something called tidal alignment. And it's a physical process that is actually quite easy to understand, right? So let's imagine that we have a large structure here, so something massive. And then we have a galaxy nearby, let's say here. Let's say that this galaxy was originally a sphere, just because we like to do that in physics. So galaxies are extended objects. And we can think about how the gravity of this object here would affect the shape of this galaxy, this blob of stars, right? And so let's think of the different gravitational forces that are acting on this galaxy. So, right, there will be gravitational attraction acting on this point in the galaxy, some gravitational force in that direction. Also on this other end of the galaxy, right? But that, right, so that'll be something that happens, right? There will also be a gravitational force in this direction, and a gravitational force in that direction, right? So let me zoom into this thing. So now let's zoom into the galaxy. I'm going to draw it like this. So we're saying gravitational forces, for example, here and here. But these gravitational forces should be slightly different, right? It should be a bit weaker farther away than closer to the object. So overall, that means that, well, this might move the galaxy closer, but in terms of its shape, what this will do is basically elongate it in this direction, right? Because it will have a differential force that kind of elongates it in that direction. Then the other, in the transverse directions, we said if we're kind of close to this object, you'll have a force that points like that in this direction, and a force that points like that in this direction. And there will be a perpendicular component of this force that tends to squash the galaxy in this direction, right? So these tidal forces, meaning the differential forces across this extended object, what they will do to this galaxy is to make it look elongated in this direction, right? It will squash it in this direction, and it will stretch it in the opposite direction. And this is very different from weak lensing, right? There's no weak lensing going on here. This is just the local gravitational field around this object, okay? And how much this galaxy gets stretched depends on the internal kind of structure of this galaxy, how strong the internal gravitational pull of the bulge of the galaxy, etc. The kind of the radial motions of the stars within it, whether they can resist these tidal forces, etc. So it's not, so you can expect this kind of effect, but it's clear, it's not obvious to know how large the effect will be, right? So the usual idea is to say, okay, remember we were talking about the inertia tensor of the shape of a given galaxy. So we think within this tidal alignment model, we say, okay, the intrinsic contribution to the inertia tensor of a galaxy should be proportional to this effect, right? Proportional to the differential in the forces of gravity across this object, right? Forces of gravity, that means the gradient of the gravitational potential, and we're now looking at the differential of that across the extent of the galaxy. So that means second derivatives of the gravitational potential, right? So we say that this should be proportional to the second derivatives of the gravitational potential itself, okay? And this is the local gravitational potential at the redshift of these galaxies, right? So this is the tidal alignment model. The tidal alignment model, what it says is that the alignment, the shapes of galaxies might receive an additional contribution from the local tidal gravitational forces. And we don't know what the proportionality factor is here, right? In weak lensing, we know what the proportionality factor is. Remember, for weak lensing, we were saying that Qij was equal to second derivatives di dj of the not the gravitational potential, but the lensing potential, right? Which is an integrated quantity, not the local one. For intrinsic ones, it's the local gravitational potential, but actually we don't know the proportionality constant here. Questions? This was, remember, from yesterday. I'm using too many q's, I think, in my notation. Qij was the integral over your image of delta theta I, delta theta j, times the intensity. The intensity of your image, right? Theta, right? The inertia tensor of your galaxy. Yep. So it's basically the quantity that we use to describe the shape of our galaxy. Yep. Okay. Say that again. What's the? Well, the source, meaning the physical origin of this effect, is the gravitational force itself. What kinds of sources are more affected by this? The theory or the kind of what we have measured so far is that the only types of galaxies that seem to have this type of alignment, or that we see are aligned, are elliptical galaxies, which mostly means, well, mostly means red galaxies. So early type galaxies, these are galaxies that don't have a, they're not spiral, so they don't have a clear plane of angular momentum where you have coherent motions like that, but you have just random motions in kind of a blob of stars, basically. And I could imagine why that. Well, there's probably several reasons why those might align more. One of them is if you have a blob of stars, maybe it's easier to deform it rather than have something with a coherent kind of motion. And the other one is elliptical galaxies. The theory is that they probably form after merger of different galaxies, and those mergers usually happen along the lines of gravitational forces, right? So you could imagine that after a merger, whatever happens afterwards might be aligned with those forces. Anything that causes gravity, right? So this, it could be just dark matter halo of something or something like that, right? Yeah. Yep. For this, yeah. So just imagine what should happen to the Earth, right? As it rotates around the sun. I'll just repeat that. So if you imagine this is the sun and this is the Earth. The Earth is a finite planet, right? If you look at the gravitational forces on the Earth, right, there should be a gravitational force on this side of the Earth and on the other side, but this one should be a bit weaker, right? So that means that the shape of the Earth should have a shearing force in this direction that kind of stretches it, right? And tidal forces in that direction, because they will have they'll be pointing in that direction, but that means that they have a component in the perpendicular direction that will tend to squash the Earth in the other direction, right? So you expect tidal alignments to squash galaxies in that direction. Yeah. Say again? Why this? Because right, so what are the forces? What's the origin of this squashing? It's the difference in the force at this point and at this point, right? So it's like force at some point in your object minus force at some point plus the extent of your object, right? And this is just the gradient of the gravitational potential at some point in your object minus the gradient in the gravitational potential at another point, x plus L in your object. So this looks like a second derivative, right, of your gravitational potential already. Yeah. Yeah. This is the second moment. Yes. Yeah. Okay. But okay, what should we expect intrinsic alignments to do to our signal? remember we said we had a massive structure somewhere along the line of sight of from our sources. That weak lensing will tend to generate tangential alignment of the galaxies, right? So this is the effect from weak lensing for any any lens along the line of sight. If this lens happens to be close to these galaxies, then you'll also have a tidal alignment effect, and that tidal alignment we said should align galaxies in the opposite direction. So this is lensing, and this is intrinsic alignments. So intrinsic alignments overall, they will decrease the lensing signal by some amount. Luckily for us, intrinsic alignments is a relatively small effect, right? Most of our galaxies are actually not elliptical; they're spiral galaxies, and they don't have a very strong alignment. In fact, as far as I know, there's been no detection of alignment of spiral galaxies. There's been tentative detections, but there's actually no evidence that they align very much. So it turns out that lensing itself is a small effect, as we saw, but the intrinsic part of the shapes of galaxies is even smaller. So depending on the sample that you're looking at, this is either a fraction of a few tenths of percent in the worst case scenario where you have lots of elliptical galaxies, but for the most part, it's kind of at the few percent level of the signal. So it's something that you need to worry about when you're looking at, or 10%. It's something that you need to worry about when you have sufficiently precise measurements of the lensing effect, but it doesn't dominate the lensing, which is good. Okay. The other thing that differentiates very clearly lensing from intrinsic alignments is the fact that intrinsic alignments is caused by the local gravitational force. Lensing is caused by the integrated gravity, right? So let's imagine the picture that we had before of cross correlations between galaxies at different redshifts, right? This idea of this is the idea of tomography, basically, being able to look at the gravitational lensing of sources at different redshifts. So let's say we have two sources, two sets of sources, one at this high redshift. Let's call that the second sample, and then another sample at low redshifts, sample 1, okay? The lensing kernel for these will be something like that. The lensing kernel for this one will be something like this, okay? So the lensing part will go with the lensing kernel. The intrinsic alignment part will be local, right? So it will go with the redshift distribution of your galaxies. It's only a local thing, right? So let's consider, for example, the autocorrelation of the cosmic shear in the first redshift bin and with itself, right? So the autocorrelation of that. So you would have several components. You would have gamma 1 lensing, twice gamma 1 lensing, gamma 1 intrinsic alignment, and then gamma 1 intrinsic, gamma 1 intrinsic, okay? And the same thing for the second one, right? So second one, gamma 2. You would have the same thing, gamma lensing, 2. You'd have the lensing intrinsic contribution, gamma lensing, gamma intrinsic. Well, you'd have the, 2, yep, that's that. Plus gamma intrinsic, 2. But then you can also look at the cross correlation between the two, right? Gamma 1, gamma 2. So what are the different combinations we can have here? That would be gamma 1, gamma 2, lensing. So this should not be 0, right? Because they both overlap in this region in redshift, right? So that cross correlation will not be 0. All right. What else? Gamma lensing 1, gamma intrinsic 2, plus gamma intrinsic 1, gamma lensing 2, plus gamma intrinsic 1, gamma intrinsic 2. Okay? So this is not 0. How about the other ones? How about this one? Gamma lensing 1, gamma intrinsic 2. should that give you a 0 or non-zero contribution? 0, right? Because gamma intrinsic 2 is sensitive to this range of redshifts only, because it's a local effect. And gamma lensing 1 is only sensitive to the line of sight integral from here, right? So this should be 0. How about this one? That's non-zero, right? Because the lensing kernel for this one goes all the way to redshift 0, so it will correlate with this redshift distribution. So that's non-zero. How about this one? The intrinsic contribution for those? 0 as well, because these two effects are local, but they are in different regions of redshift, right? So they will not correlate with one another. Remember the Limber integral, which I think I might have actually in the next slide, right? It's sensitive to the product of the two kernels. And so if your two kernels are this, and they're separated, then the product of the two is 0. So you should get no correlation between them. Yeah. Yeah. Yeah, yeah. So, so let me finish my point, and then I'll go to this. So my point here is that if we believe this argument, then by comparing the autocorrelations with the cross-correlations, you should notice that there's a component that contributes to the amplitude of these autocorrelations that is not there in the cross-correlations, because several of these terms drop out. So that allows you to diagnose if you have intrinsic alignments in your data. The caveat is if your redshift distributions are very uncertain and you're not sure whether this is your redshift distribution or this is your redshift distribution, then that spoils the argument, right? Because you will have correlations between them that you wouldn't expect otherwise. So controlling intrinsic alignments also depends a lot on how good your photometric redshifts are, and we'll talk about those tomorrow. Other questions? Yeah. Yeah. Yeah, which you don't? Yes. Yeah, but you don't know exactly what. You could, yeah. And in other words, so one thing, maybe what you're saying is one thing you could do is you have samples of galaxies at different redshifts, and maybe what we should do is only consider cross-correlations where we can keep these contributions under control. But that throws away a huge amount of data. So what we want to do is not that, but try to use all the different auto and cross-correlations, and yeah. Yep. Yep. It's just proportional to the redshift distribution of your galaxies, basically. That's it. Yeah. Yes. Yeah. You don't. It's not like you get confused, right? It's just what structure is contributing to each of them, and so here you will know which of these terms need to drop out, I guess, right? Yeah. Well, not just only lensing, right? You will always have this contribution, for example. So intrinsic alignments. No, this comes from tidal alignment of these galaxies, which is correlated with the local large-scale structure and the fact that this lensing is sensitive to this local large-scale structure as well, right? Because part of this large-scale structure is lensing these photons as well. So, yeah. What you're saying applies a lot also to the cross-correlation between lensing and galaxies, right? And the overdensity of galaxies. The overdensity of galaxies, as we will see tomorrow, is local. So that's using cross-correlations with the local density of galaxies is another way to try to keep intrinsic alignments into under control, basically. It's a way to self-calibrate, let's say, intrinsic alignments as well. Yeah. Yeah. Mm-hmm. Yep. Yep. So I'm not saying that any combination here is completely immune to intrinsic alignments. I'm saying that intrinsic alignments will affect autocorrelations and cross-correlations differently. So you can use that as to diagnose whether you actually have very strong intrinsic alignments or not. So it's part of, by forward modeling it, this effect allows you to separate the intrinsic alignment part intrinsically, like internally in your likelihood from the shear part, right? There's something specific about intrinsic alignments, which is the fact that it's local, whereas the lensing is not. Well, depends on how big your intrinsic alignment effect is, right? But yeah. No, you don't know, but my point is that what's going to be your model, right? Your model for this power spectrum is that your kappa field is the kappa from lensing, which you know exactly, plus the kappa from intrinsic alignment with a free amplitude that you don't know, and you need to infer that from the data, right? If we didn't have this effect, that intrinsic alignments is local but lensing is not, this would spoil the game completely, because then what you care about is the amplitude, using the amplitude of this thing to constrain sigma 8, for example. But if now you have another amplitude that is completely free and is degenerate with sigma 8, you're screwed. You can't do sigma 8. But what I'm saying is the reason why internally you will be able to put a constraint at the same time on A and on sigma 8 is the fact that these two respond differently in cross-correlation, basically, right? Yeah. Yeah. So it's the problem is that we don't know the amplitude of intrinsic alignment, so we need to marginalize over that. Yeah. Yeah. Any other questions? Okay. So the next big challenge for cosmic shear is the fact that it's very sensitive to small scales, and this is easy to understand. Again, remember the the Limber equation there, right? So your CL at a given angular scale L is sensitive to physical scales that go like L over chi. So if your chi is very well defined, then you'll be able to connect an L with a K. Okay, so we'll be able, for example, to throw away small scales where the modeling of the matter power spectrum is dodgy, okay, for example. However, in weak lensing, we have a problem, right? Because this lensing kernel, it extends all the way to redshift 0, always, because you're always sensitive to all the large-scale structure down to redshift 0. So again, we have a redshift distribution like that. The corresponding, thanks, Rogerio, lensing kernel will look like that, and will extend all the way to redshift 0. Okay, so one immediate caveat for weak lensing is that you're not going to be as sensitive to evolution of any quantity in redshift just because you're averaging over quite a lot of redshifts by looking at lensing, but we have to deal with that. That's okay. But it will be more sensitive to small scales, right? Because you always have a contribution in the lensing kernel from low redshifts, right? So what does that do to the angular power spectrum? So this is a complicated plot. This, in the x-axis, you have a 3D wave number. And in the y-axis, you have the contribution to the cosmic shear power spectrum at a given angular scale L from the power spectrum at a given physical scale K. Okay? So in the background, just to guide the eye, you have the shape of the matter power spectrum. And remember, these are linear scales. This is definitely very nonlinear scales. And here you have a contribution at L equals 100. We said that this is of the order of 2 degrees, more or less. This is a very large scale on the sky. And you see that even at those scales, you have contributions on relatively small scales, right? You have a significant contribution at K of 1, which is a very nonlinear scale. And this is, what you're seeing here, this is the tail of the lensing kernel towards redshift 0. That's what this is. Then when you look at Ls of 1,000, so this is a 1/10 of a degree, it's actually not that small a scale, and it's routinely used in weak lensing analysis. There you're definitely always in the nonlinear regime and probably getting a lot of contribution from fairly nonlinear scales. So that means that, for weak lensing, you get a significant contribution from structure at low redshifts and small scales. Okay? So you need to make sure that your modeling of the power spectrum is correct there. That's why we tend to use emulators based on simulations rather than relying on the Halo model necessarily to model that, right? As we said. But there's a related problem, which is baryonic effects. So about 16% of all the matter in the universe is baryonic matter, which is not dark matter, which means that it's subject to non-gravitational forces. And that means that it's not going to cluster exactly the same way that dark matter clusters, right? That would be fine if we could simulate baryonic matter easily, because we just put that in an embodied simulation, let it run, and you're done. But it turns out that an embodied simulation for just dark matter, which just feels gravity, is very easy to run. You don't need to worry too much about that. It's just gravity. But if you have baryons, you need to worry about all kinds of hydrodynamical processes that happen, right? And those, as Paco, I think, mentioned yesterday, those happen on really, really small scales that you cannot simulate. But they have repercussions on much larger scales that you are sensitive to. Not sure if I have an image. No. A typical, and this is probably the most pernicious effect that we have, the most pernicious baryonic effect that we have is what happens, what's called AGN feedback, right? So in the centers of galaxies, you have these supermassive black holes that accrete a lot of matter and energy from the galaxy, and then they spew huge amounts of gas, and also they spew huge amounts of energy that actually can displace all the surrounding gas to very large distances, right? In an embodied simulation, we can't simulate an AGN, an active galactic nucleus. That's too small a scale. So we have to put in ingredients in the embodied simulation by hand, where we say, I think based on the mass of this galaxy, the AGN should be like this, and probably this is the amount of energy that it's spewing, and what that does to the gas, right? So we need to put in parameters by hand that are not fundamental, right? So there's a huge uncertainty in how gas actually clusters, right? And so when you're trying to make predictions for the matter power spectrum at with percent level errors, just to give you an idea, this is what a cosmic shear power spectrum looks like for DES year 3. So this is a much crappier version of what LSST will be able to do. And it's still quite accurate, right? You can measure the power spectrum with quite a high accuracy. Remember, I was saying this is noise dominated beyond this regime. And LSST will be noise dominated beyond this regime, but still, even if it's noise dominated, you can measure the power spectrum really well. So you're trying to measure the power spectrum with an uncertainty of 1%, but now you have 15 to 20% of your gas is actually behaving in a weird way, right? Of your matter is behaving in a weird way. That's gonna matter. So just to show you how much it matters, this is a typical plot you look at when you worry about baryonic effects. So this is as a function of wave number, the ratio between the matter power spectrum in a simulation that includes these baryonic effects, and the matter power spectrum in a simulation that just has gravity, no baryons. And so what you see is that at scales k roughly equals 1 or so, beyond that scale, you have a suppression in the amount of power, right? All these curves are smaller than 1. This mostly comes from all this gas that has been ejected by the AGNs on small scales and just essentially loses a lot of. So you lose clustering on small scales due to the spewing of the expelling of the gas due to AGN feedback, among other effects. But here's how annoying this is, right? So these lines, they're all predictions from different hydrodynamical simulations. This is how not well we understand baryonic effects, right? You're seeing that these are effects at the 30% level. And we can't really, these are all simulations that are presumably, most of the gas physics in the simulations, or the gas observables in the simulations, they match observations. But for all of them, you can get to predictions of the matter power spectrum that vary on small scales by about 30%. If we take weak lensing data and we say, okay, let's say that we understand cosmology perfectly as it comes to us from the CMB. So we fix that, and instead, what we want to do is we use weak lensing data to say how strong baryonic effects are. These are the kinds of uncertainties that you get from current weak lensing data, which is the same order of magnitude. That's the color bands. So again, 20 to 30% uncertainty. So we're trying to measure the power spectrum at at 1% level, but our current uncertainties on this model on baryonic effects are at the 30% level. So the way forward, I don't think I have a slide on that. No, the way forward for this seems to be we just need to model this, right? We need to model baryonic effects. We need physical models for what AGN feedback does. They should be, first of all, physically sensible. They should be able to reproduce all the different results from hydro simulations. And the idea would be to measure the free parameters of those models as part of our constraints from weak lensing, right? So we need to forward model those and marginalize over this level of uncertainty. Yeah, so that's the way we hope we can deal with baryonic effects. And there's maybe tomorrow I'll be able to mention some other ideas, but yeah. Yes, yes, exactly. This DMO is the nonlinear power spectrum already, right? Yeah. Mm. Yeah. Yes. So you're not going to go back to the linear power spectrum. This is a much smaller effect than going from the linear to the nonlinear, but it is a suppression. The point is that this one, right, the DMO, dark matter only power spectrum, we know this really, really well. We can model this from gravity only simulations at the 1% level if we have to, right? So that has no uncertainties in it. So we don't really worry about the nonlinear effects because from a simulation we have those under control. The problem is that this one has a lot of uncertainty in it. Yeah. This is not an unsolvable problem, right? Actually, now we already have physical models that people have implemented and shown that they actually reproduce the results from loads of different hydrodynamical simulations. So the models that we seem to have are quite flexible, right? They have enough free parameters that allow us to match all these different hydrodynamical simulations. The problem is that when we marginalize over all of this, we will lose sensitivity on cosmology. So it'd be great if we could actually have an external way of calibrating this effect, right? So that we wouldn't have to marginalize over so much of it. Yeah. Does that make sense? Any questions? Yeah. Yeah.
So does that affect like the measurement accuracy of the
Yeah. So this is a very good question. So the question, I'm going to rephrase your question saying, couldn't you just remove some of your scales to deal, to be less sensitive to baryonic effects? And I think with current data, where the uncertainty on small scales is fairly small, but still sizable, maybe you can get away with that. You can cut, let's say, at L of 1,000 or L of a few hundred, and then maybe you'll be a bit less affected by baryonic effects. But as soon as you start getting smaller error bars here, I think you're always going to be affected by this curse of weak lensing, which is the fact that you're always affected by small-scale structure at redshift 0. So for LSST-like sensitivity, if you wanted to play that game, right, if you wanted to throw away all scales where I know my final constraints are not going to be affected by baryonic effects, I think that means effectively you would need to cut anything that is at L larger than 100 or something like that, because your error bars are so sensitive for LSST, just so small. So that means you lose, like, you increment your final constraints on your final error bars on cosmological parameters by a factor 10 or something like that. Like you lose all sensitivity. So I think we should do better than that, right? We should maybe try to model baryonic effects and extract as much information as we can. What time is it? Okay, we have 5 minutes, and in these 5 minutes, I'm going to finish with weak lensing, talking about the last topic that I wanted to mention, which is the other type of weak lensing that we have, which is CMB lensing. Okay, this is something that that Manu will talk about in more detail, I think. So I won't go into the math of it too much. But what's the idea behind behind CMB lensing. We saw that lensing doesn't really change the intensity, right, of any given image, meaning that it doesn't lose or create photons, right? The number of photons gets conserved by lensing. What it does is it displaces those photons, right? The intensity of the CMB, you can always relate to the temperature of the CMB. So just think of the temperature of the CMB as some kind of measurement of its intensity. So how come lensing is an effect that we should take into account? Well, as we said, lensing will not create or change the energies of photons, for example, but it will move them around. So the temperature of the CMB, the map of the CMB after lensing, so that's going to be the lensed CMB, should just be the unlensed CMB. But it should be the unlensed CMB at a different position, right? At the position before lensing. So at n minus what I call delta theta, so the deflection angle from lensing. Okay? We saw that this was the angular gradient of the lensing potential. All right, so the deflection angles are relatively small, so we can do a Taylor expansion here and say that the lensed CMB will be the unlensed CMB, at the original position. And then if we Taylor expand, we get minus gradient of t dot product with the displacement vector. And the displacement vector, we said, was the gradient of phi L. Okay. All right. So this already tells us something about what lensing does to the CMB, right? It gives it a contribution that looks like this. And what we can think of this contribution in two different ways. First, we know that the fluctuations in the CMB, the temperature fluctuations are Gaussianly distributed, right? They have a Gaussian distribution. But so this will be Gaussian. Here you have a product of two different fields. You have the Gaussian CMB fluctuations, the gradient of that, but that's still Gaussian, with another field, which we might, this is the lensing potential, we might think of it as a Gaussian field as well. But the product of two Gaussian fields is not a Gaussian field. So weak lensing will generate non-Gaussianities on the lensing map. Oh, sorry, on the temperature fluctuations map. So this is one way of thinking about weak lensing as something that gives you higher order correlators in your CMB map. The other way to think about that, which I think is maybe a bit easier to understand, is we have two effects, right, along the line of sight. We have the temperature fluctuations, which basically come mostly from the redshift of recombination, so Z LSS. And then we have the lensing effect, which is all the way along the line of sight from that, right? You know, for the most part, these two are not really correlated with one another. So you could think of this as some kind of screen that is in between you and the lensing fluctuations that is completely uncorrelated with the temperature fluctuations. So it's completely uncorrelated with those. So in a sense, you can think of this as an external piece of junk that is breaking the statistical homogeneity of an isotropy of the temperature fluctuations. So this is a term that will break statistical isotropy in that sense, right? So if you think of this as a fixed field, then your lensed field is no longer statistically isotropic because this imposes some extra crap in your data. And so, for example, we saw that correlators of statistically isotropic field should be diagonal in Fourier space, right? So the correlator of the temperature fluctuation at an angular scale L and an angular scale TL prime should be proportional to delta L minus L prime, right? But that's only if they're statistically isotropic. Otherwise, if you break statistical isotropy, then you might have non-zero correlators of the form TL T times L plus some extra scale big L or something like that, right? So you'll have what we call off-diagonal and these are generated by the lensing potential. So the idea in CMB lensing is that you look at off-diagonal correlators like this and use those to reconstruct the effects of lensing. I'm not going to tell you how, because I think Manu will cover some of that, and he'll have more time to do that. But that's the idea. The idea is using the temperature fluctuations in the CMB, looking at off-diagonal correlators like that, to extract a map of the lensing convergence all the way to the CMB. And so why is that useful? Very quickly, the way we should think about it for practical purposes is that the CMB lensing is just another. It's like lensing for galaxies, except all our galaxies now are at very high redshift. All the galaxies are at the same redshift, which is redshift of 1,100, the redshift of the last scattering surface. And so this basically shows you what the lensing kernels look like for galaxies at different sources, at different redshifts. So, as Miguel said before, if you have galaxies at some redshift, the lensing kernel will kind of peak at intermediate redshifts. Well, with CMB lensing, then what you get is another set of quote-unquote galaxies, which sit at a much higher redshift at a distance of about 14 gigaparsecs. So it's basically a map that will correlate with all of the large-scale structure of the universe. And there's a few advantages of CMB lensing compared to galaxy lensing. So based on the caveats that we talked about, what do you think are the main advantages of CMB lensing compared to weak lensing? You have a larger fraction of the sky. Yeah, that's true. Baryonic effects. Yeah, so you're less sensitive to baryonic effects, and that's because most of the lensing kernel actually peaks at higher redshifts, and so you can separate small scales from large scales a bit better because you're less affected by the low redshift small scale stuff. So that's true. So the autocorrelation, at least, of the CMB lensing potential, or kappa, is less affected by baryonic effects, so that's a good point. What else? Yeah, so CMB lensing doesn't have intrinsic alignments. And in fact, cross-correlations between lensing and CMB lensing might be used to calibrate intrinsic alignments, for example. So that's another advantage. Exactly, yeah. And I think maybe Manu will tell you the bad things about CMB lensing, but I'm not going to do that. Cool, all right, so that's it for lensing. We'll talk about galaxy clustering tomorrow. And I'm not going to be able to cover Sunyazelovich because this is taking me too long. But I think Manu is also going to talk about that, so hopefully you'll get a picture of that as well. All right, okay, thank you.
Thank you, David. Tech questions for David? Yes? Ladies first.
Okay. Can you explain again at which scale of the CMB power spectrum are more affected by the lensing?
Yes, I can, but I think Manu will do a much better job than me. I think the idea is, if we didn't have the effects of lensing, what we would see is temperature fluctuations, which are statistically Gaussian and also statistically isotropic, right? Correlators of the Fourier modes of that field on different scales should be 0, basically, right? Okay, but lensing will distort those, so it will give you a distortion, which will break that statistical isotropy. The easiest way for me to see it is by doing this kind of Taylor expansion and seeing that there's a term here that breaks statistical isotropy, because this is basically a fixed map with particular blobs in a particular region of the sky where there's more lensing than other blobs, right? And so that's what it does. I should have put a figure here of a simulation where you have a lensing potential and then the temperature fluctuations, and you can see how that perturbs those temperature fluctuations. But anyway, yeah. So this will basically generate off-diagonal correlators in the temperature fluctuations, because now they're not statistically isotropic anymore, and which sounds bad, but in reality it's a good thing. So what it does is that you can actually use those off-diagonal correlators, where you take a Fourier mode or a harmonic mode and correlate them with a different harmonic mode, and from those extract. So this actually you can show, and I think maybe Manu will show you this. If you average this over many realizations of the temperature fluctuations, this will be proportional to the lensing potential at a scale L, basically. And so you can use these correlators to reconstruct the lensing map itself.
And if you want to delens the power spectrum, you have to create this potential map.
Yeah, so that's interesting. If you wanted to delens the temperature or the CMB power spectrum, there's different ways of doing that. One thing you can do is you can get an estimate of what you think the lensing potential should be. One way of doing that would be to use large-scale structure to infer something about the lensing potential. And basically, you subtract a term like this. So you take your fluctuations, compute the gradient, dot product with that, and then remove this contribution. That's one way of doing that. There's this idea of doing internal or iterative delensing, where you use your CMB data to infer the lensing potential. You use the lensing potential to delens so subtract this thing, and then you do it again until you refine your estimate of the lensing potential. And that I'm not an expert on that, but that's kind of the idea. So that idea of delensing can be useful for the temperature fluctuations, because I'm not sure if Manu actually mentioned this, but these BAOs in the temperature power spectrum, lensing makes them a bit less, the amplitude of those, it kind of dampens them, it makes them less prominent. So if you can sharpen them out, you can get slightly better constraints on cosmological parameters. But where it's really important is for the polarization of the CMB. I think Manu maybe will mention this today. There's these E modes and B modes of the CMB polarization. The B modes are super important for the tensor fluctuations. But lensing will put a bunch of E modes into the B modes, so it will put a bunch of crap there. And if you can remove that by doing delensing, it can be super beneficial, basically. But yeah.
Yeah, thanks a lot for the lecture. I might have missed this, but when you showed the expression for the shear field in terms of the plus and cross components, are those related to the E and B mode decomposition?
Not really, no.
Okay.
One would like it to be the case, but no.
Yeah, because I think they were in the same image. Yeah.
Yeah, so they're not exactly, well, yes, sorry, that's because I copied this from that paper. So in the paper, you will see the definition of E modes and B modes. So basically, okay, cosmic shear is a spin-2 field, right? It's something where for each galaxy you have a measure of something that has an orientation but not really a direction, right? So it's a spin-2 field. The polarization of the CMB is also a spin-2 field that has, it tells you where the direction of the polarization of the photons is and the amplitude of that polarization. So the same idea of splitting the polarization of the CMB into something called E modes and B modes, which are scalar, scalar potentials of this vector-like field. That also applies to weak lensing, so you can also do that. But no, gamma T, gamma cross are not directly E modes or B modes. Some of the correlators involving gamma T and gamma cross involve the E modes or the B modes in different ways. So this psi plus, psi minus, they're mostly affected by the EE power spectrum. Turns out that the E mode for weak lensing is exactly the same as the convergence field, which is kind of nice. Gamma T, gamma cross, for example, I think that's proportional to the cross correlation between E modes and B modes, so it should be 0.
So that was actually my question. If the cross correlation vanishes for the same reasons,
exactly.
the symmetry of the.
So the cross correlation of gamma T, gamma cross, I think, is affected only by the EB power spectrum. If you correlate gamma cross with the positions of galaxies, that should be proportional to the correlation of the B mode lensing with the density field, for example. So that should also be 0. So that's how you can have some diagnostics to see which. To see if you have a B mode component in your lensing field, which for lensing it should be exactly 0. Yeah.
Thanks a lot.
Yeah.
So I forgot to mention that we don't have a Q&A session today. We have this colloquium.
Yeah.
So please ask questions.
Yeah.
Thanks for the lecture. Can we combine, make a 3x2 point with like LSST surveys, normal surveys with CMB lensing because with CMB because CMB will be like a very thin beam at redshift 1000.
Yeah. So you can definitely combine weak lensing from galaxies with weak lensing from the CMB, not with the CMB itself, because the CMB only receives contributions from redshift 1000, except for the ISW. The ISW maybe you can integrated Sachs-Wolf effect. I think Manu talked about that yesterday. But with CMB lensing, for sure, and it has these advantages that we discussed that, well, first of all, CMB lensing should be unaffected completely by intrinsic alignments. We had this problem that I wanted to talk about tomorrow, that for weak lensing, another problem you have is that you need a model for the redshift distribution of your galaxies, right? And if you don't have, if you have strong uncertainties on the redshift distribution, that will propagate into your power spectrum. For CMB lensing, you know exactly what the redshift distribution of your sources are, right? It's just delta function at z equals 1,000. So that's another advantage of that. So you can use that actually to potentially cross-calibrate some aspects of these redshift distributions in the cross-correlation with CMB lensing.
And why is the kernel of the CMB peaked at like almost at the distance of the CMB?
Yeah, so that's a bit confusing. It has to do with how I've plotted this. So
I would expect a peak at the middle.
Yeah. So remember the lensing kernel. I'm going to write it again here. Goes like this, right? So Q is proportional to chi over A of chi times chi S minus chi divided by chi S. So this is a constant. This doesn't change the shape, and this is a parabola that peaks exactly at half of chi S. So you would expect that this should peak at half of, at 7 gigaparsecs or something like that. But you have this factor A of x, A of chi. This is here because this is a factor of 1 over A is what transforms the gravitational potential to the density field. So I have this A here because I've expressed my kappa field in terms of delta rather than the gravitational potential. This A is of order 1 at low redshifts, but at high redshifts is of order 1,000. So it's this weighting by A that shifts that peak over there, right? But that doesn't mean much, right? I mean, so the CMB lensing map will still have a very strong contribution from all these low redshifts. So you cross-correlate with the CMB lensing, and you'll definitely see a correlation between low redshift stuff and the CMB lensing, even if it nominally peaks there.
Okay, thank you.
Yeah.
David, I have a question. Just now you mentioned you have some model to model the distribution of the redshift. What usually we model this distribution?
How we model it?
Yeah.
Maybe let's talk about that tomorrow, because that's part of what I want to mention tomorrow.
Yeah,
actually.
I have another question.
Yep.
Because why the redshift space distortion will not affect this lensing?
They will not affect this lensing because you're not sensitive really to the position of these objects very much, right? You just care about the objects as tracers of the lensing field itself, right? So you're not really using the statistics of their positions, like how correlated their positions are, just how correlated their measurement of lensing is across those, right? So for weak lensing, there will be no effect. If you're correlating the positions of galaxies with lensing, then there could be a contribution from redshift space distortions that you need to worry about. But if it's just lensing on its own, you only care about the positions of these galaxies as the positions at which you have measured these fields. But that's it. You don't really care about where they are in space very much.
Okay, thanks.
Yeah.
Okay, so let's thank David for this very nice lecture.
Thank you.
So we reconvene at 11.